In the last lecture, we had introduced the concept of electric field and talked about Coulomb's law as well as the principle of superposition. That is, when there are multiple charges which produce electric field at a point, we had said that the effect is essentially a linear sum of the effects due to each individual charge. And we had also talked about what happens in a continuous charge distribution, where we wrote down an expression for the electric field in terms of integrals which involve the charge density at a point. In this lecture, we will be trying to talk about essentially two ideas. The first one is known as Gauss's law, which is essentially a law very similar in content to the Coulomb's law. And we will see that in spite of the fact that Coulomb's law and Gauss's law are essentially equivalent statements, but under certain conditions it is much easier to use the Gauss's law. But before we do that, let us introduce the concept of a flux. The flux essentially comes in the same way as when, for example, you have a flowing water. Now, when a flowing water passes through a surface, basically the amount of flow that goes out of that surface, it depends upon not only the velocity of the flow, but it also depends upon both the area and the orientation of the area to the direction of the velocity. Now, exactly the same way we define the flux of an electric field. So, you recall that we had talked about the area being considered as a vector. So, if you look at an arbitrary area, then you could consider an infinitesimal part of it. The outgoing normal to such an infinitesimal area is the direction associated with such an area. It of course, has a magnitude. So, in that sense, an area, though it is two dimensional, one can consider it as a vector. It is a vector, however, there is a convention associated with it, namely that of the outgoing normal. Now, in this particular example, what we are showing, for instance, is a surface, and there is an electric field which is coming, and so the direction of that surface is perpendicular to this S, and as a result the electric field makes an angle with the direction of that surface. And one defines the flux of the electric field as surface integral of the dot product of the electric field with the area element integrated all over. So, in other words, if you look at a particular point where the area element, the vector, the normal vector is making an angle theta with the electric field, then the definition of the flux would be integral of S E ds cos theta. So, this is what we are going to be talking about. But before we continue with it, we would like to introduce what is known as a solid angle. You are all familiar with the concept of an ordinary angle. You recall how does one define an angle in two dimension. Now, an angle in two dimension is defined by, so it is something like this. So, supposing you have this angle. So, what is this angle theta? This is, you draw an arc there, and this angle theta is related to this length of the arc and this radius. So, if this is radius r, then r times theta is this length of the arc. In other words, you define this angle theta measured in radians as the ratio of the length of the arc to the radius. The only thing that you should recall is that this arc is a part of a circle. So, for instance, if you did not have this as a part of the circle, but you had a curve like this, then I could still define this angle theta by saying that I take the projection of this arc along the normal. Now, recall that in spite of the fact that an angle being ratio of two lengths, r theta by r, is dimensionless, we still conventionally measure it by using, if you like, an unit called degrees or radians. So, this angle theta in radians is given by the length of the arc divided by the radius. Now, the concept of a solid angle is essentially very similar. So, what we do is this, that suppose I am looking at what is the angle, what is the solid angle that an area makes at a particular point P. Now, what I do is this, I draw tangents from that point onto this area, and remember, if I take this angle to be small, then the direction, so I have the following thing, that the direction of the length, which I take to be infinitesimal, is perpendicular to the direction of perpendicular to this surface, and this is the direction r, which is essentially joining P to that element and extending it, and this angle is alpha. Now, one defines the solid angle d omega made by this area element, which is infinitesimally small area element, as the projection, the perpendicular component of this surface, divided by r square, which means that since I am taking the projection perpendicular to this r, this is ds cosine of alpha divided by r square. So, once again you notice that d omega and hence omega is dimensionless. In spite of that, we measure it in terms of an unit known as steradians. Just to look at this a little more in detail, let us look at, let us suppose I have a cone, I have a right circular cone having a vertical angle half semi vertical angle equal to theta. Now, let me make a statement, these red things that you see, these are the direction of the electric field which is threading through this cone. From the base of the cone it enters perpendicularly and leaves through the slanted surface of the cone. Now, I am interested in calculating how much is the flux coming out of that cone. Now, before we do that, please note that this cone has essentially two surfaces. So, let me draw a cone here. So, there is a base there, and since we define n as the outward normal, that would be the outward normal of the base. Now, suppose I am interested in finding out how much is the flux through this base. So, this we have seen is integral of E, instead of dot ds, let me write a dot n ds. Since the electric field is constant and has a magnitude E, it will come out of this sign. So, basically, and the second thing that you notice is the direction of n and the direction of E are opposite to each other, because electric field is entering the base. So, as a result, this E dot n is nothing but minus the modulus of E, and I am left with only the integral over d s, and assuming that r is the radius of the base of the cone. So, this is nothing but minus E times pi times r square. The reason why I have a negative sign is because in my definition I had talked about outward flux, but as you can see from the picture, the electric fields are threading into the cone. As a result, the net outward flux through that base is negative. However, let us look at what happens if I look at the slanted area. Now, actually speaking, we could supposing it were a water flowing through, you could have got an answer to that without even working it out. The reason is whatever water is entering through the base must leave through the slanted surface of the base, and as a result, if the flux coming in is E times pi r square, the flux going out through the slanted surface must also be equal to E times pi r square. Let us look at whether that is correct or not. Now, what we do is this. Let us consider the following. Let us take a strip. Now, this is a strip of radius small r. This is a strip of radius small r and width d l, length and width will be d l at a distance at a height h below. Okay. Now, so if I do that, look at this, the how much. So, I have a length L and radius small r here. Now, so let us look at this. What is E dot d s? The E dot d s is of course the magnitude of E. The area of that strip, which is equal to 2 pi r, because r is the radius there, times d l, which is the slanted width. And the second thing is that the angle which the normal to the slanted surface is making with the electric field is obviously pi by 2 minus theta. So, I get 2 pi r d l cosine of pi by 2 minus theta. So, let us write it again. So, E dot d s is equal to magnitude of E 2 pi r d l times sin theta. Now, let us look at this. So, let me redraw this picture on this. So, I have taken this strip here. This height here is h, this angle is theta, and this is of course r. I can immediately look up a relationship between them. You can see that what is r, what is the relationship between L, h and r. So, r is obviously equal to h tan theta, and L, which is this length, is equal to h by cos theta, because this is h. So, L cos theta is h. So, it is h by cos theta. So, if you plug them in here, what I get is E dot d s is equal to magnitude of E times 2 pi, and of course, I have got r d l sin theta. So, therefore, you notice there is already a sin theta by cos theta here, and I have got this thing. So, I get h square times tan theta. Okay. Now, the tan theta is actually constant. Tan theta is actually constant, and so therefore, what I get here is this. So, what is my flux phi? I have to only integrate this quantity there. So, therefore, what I get is, after integration, I get E magnitude of E times, if you do it properly and put in the relationship as we have done in the slide, times pi r square. This is the flux through a cone, but then I already knew the answer, that if the amount of flux that is getting in is E times pi r square, the amount of flux which is going out should also be E times pi r square. Okay, let us look at some results that is coming out of this. Let me take a sphere of radius capital R, and let me put a charge q at the center of this sphere. Now, I already know that the lines of forces, which are the directions of the electric field due to this charge q, are all symmetric, and if I have, since I have got a sphere, these are all perpendicular to the surface of the sphere, and I am only interested in the electric field on the surface of the sphere. Now, since the direction of the electric field and the direction of normal to the surface are parallel, the flux E dot ds is nothing but the E times ds, and when I integrate, now remember that electric field strength is the same all over at all points on the surface of the sphere, namely it is equal to 1 over 4 pi epsilon 0 q by r square. So, that is my strength of the electric field, and since the electric field strength is the same everywhere, the integral is only over the surface, which gives me 4 pi r square, that is the area of that surface, and if I now calculate it, it becomes q by epsilon 0. Notice that the amount of flux, I put in a charge at the center of the sphere, single charge q, the flux coming out of the surface is simply given by q by epsilon 0, which is independent of the radius of the sphere. Let us proceed with little more. We already introduced the concept of a solid angle. Now, suppose I had a surface of arbitrary shape, and there is a charge q, that I have kept somewhere inside that surface. Now, notice, supposing I am interested in calculating the flux through the surface. So, what I do is this, I need to calculate electric field at every point on this surface. So, let me take an infinitesimal surface area ds at a distance r along the vector r from the point q. Now, what I do is this, using this surface area, I connect them to alt q and find out the solid angle d omega that this surface element ds makes at the point q. Now, let us look at what do I get out of it. Now, so far as the electric field is concerned, the electric field at the distance r is q by 4 pi epsilon 0 1 over r square along the radial direction, along this direction. I have to now take the dot product with ds. So, I multiply with ds times cos theta, whatever is the angle that it makes here. But you remember that ds cos theta is nothing but the projection of this area element ds in a direction perpendicular to the r. So, that is nothing but in our previous notation d s perpendicular. So, as a result what I get is that d s perpendicular divided by r square, that gives me d omega. So, the d phi is q times d omega divided by 4 pi epsilon 0. So, notice that the flux due to the area element d s depends only on the solid angle that it subtends at the point q. Now, when I do the integration, all that I need to do is to take the area element all over the surface, and you notice that every place the direction of the radial direction is outward, and the normal to the surface will make an acute angle with it. And as a result, I get the total solid angle that is subtended at the point q, which obviously is 4 pi. So, that I get the total flux equal to q times 4 pi divided by 4 pi epsilon 0, namely q by epsilon 0. Now, let us suppose this charge q is not inside that surface, but is outside that surface at this point. Now, I do exactly the same thing, but notice that the radial, if you draw rays from this point q, it will cut the surface in two places. One is here, let us call it d s 1, another is here, that is called d s 2. The normal direction to this is that way, whereas the normal direction to this one is in the opposite direction. Now, so as a result, as you go around this surface, for every positive solid angle, there would be a negative solid angle, and the net effect would be 0. So, what have we actually got? What we got is that integral of E dot d s over a closed surface is equal to q by epsilon 0 when the charge q is inside the surface, and is equal to 0 if q is outside. Now, this is in general true if I have multiple charges as well, because the principle is the same, it is a superposition principle. So, what you actually find is this, that the flux phi, electric flux phi, which is the same as the integral E dot d s, is given by the amount of charge that is enclosed by the surface divided by epsilon 0. This is the statement of Gauss's law. If there are no charges enclosed inside, it is equal to 0. If there are some, then of course, you have to simply talk about the amount of charge that is enclosed. So, that is my Gauss's law, stated in the form of flux phi, which is integral E dot d s. Now, let me now recall for you that suppose this surface S encloses a volume V. So, this integral E dot d s by divergence theorem is same as the integral over volume V, and the surface integral will become a volume integral, and I will be left with del dot E, that is divergence of E dV, and that is equal to the amount of charge that is enclosed divided by epsilon 0. The amount of charge that is enclosed can be written as integral over the volume the integration over the density now, since this is true for an arbitrary volume, I get a corresponding differential statement of the Gauss's law, which says del dot of E is equal to rho by epsilon 0. So, this is the differential form of the Gauss's law. So, let us do a little bit of detailed arithmetic and try to see whether one can directly derive it from Coulomb's law. So, for that I need the expression of Coulomb's law for a continuous charge distribution. So, notice that we had earlier written down the electric field E is given by 1 over 4 pi epsilon 0, this is electric field at a point r, integral over the volume rho at an arbitrary point inside that volume r minus r prime vector by r minus r prime cube, and the integration is over the primed variable. So, if I want now del dot of this, if I need the del dot of E, this, remember this del operator is with respect to the variable r, which is the point at which I am trying to find my electric field. So, this can be written as 1 over 4 pi epsilon 0 integral over the volume, rho r prime does not have any dependence on r, it is a quantity dependent on r prime, and then I write down del dot of r minus r prime divided by r minus r prime cube. Now, so this is del dot of this thing. Now, I can do a bit of a sleight of hand, and I notice that this quantity here depends on r minus r prime. So, instead of doing the derivative over the variable r, supposing I am to take the derivative with respect to r prime, then all that I need is just a minus sign. So, therefore, I put a minus sign here and put a prime there. So, the difference now is that this quantity now is del prime dot r minus r prime divided by this. Okay. Now, this is equal to minus 1 over 4 pi epsilon 0 integral over the volume rho r prime del prime dot. Now, notice this is essentially a vector like vector r by r cube. So, I can write it as a gradient. I can write it as a gradient, but because I am writing it as a gradient over the primed variable, I do not pick up that minus sign. So, this is del prime dot del prime of 1 over r minus r prime dq r prime. But this is nothing but del prime square. This is nothing but del prime square. So, this is equal to minus 1 over 4 pi epsilon 0 integral over the volume rho r prime del prime square of 1 over r minus r prime dq bar prime. If you recall, when we talked about the Laplacian operator, we said del square of 1 over r, this is a magnitude, is equal to minus 4 pi times the delta function. This is actually a 3-dimensional delta function. So, therefore, this quantity here is minus 4 pi times delta function. Now, since the delta function is a 3-dimensional delta function, I indicate it by delta cube r minus r prime. But once I have a delta function, this integral is easy, because at all points other than at r is equal to r prime, the delta function vanishes. So, I only have contribution from r is equal to r prime. There is already a minus sign, 4 pi cancels. So, I will be left with 1 over epsilon 0 times rho of r, which is exactly what we derived using the definition of the flux. But you notice this is hard work. Let me illustrate the calculation of flux taking a few examples. I have here a cube. Now, I have a cube, and at the corner of the cube, I have put a charge q. But before I illustrate this, notice a couple of things. The physical content of the Gauss's law is the same as that of the Coulomb's law. There is nothing more, nothing less. However, we can sometimes use Gauss's law to our advantage, particularly where the symmetry makes it easy for us to write the left hand side, namely integral E dot ds, as a function, explicit function of the electric field E. Now, then if I can calculate that, I can get an expression for the electric field. This obviously cannot be done excepting in cases where there is significant amount of symmetry, and that is exactly what we are going to talk about now. For instance, let us take first a cube. Now, supposing I put a charge q at the center of the cube. Now, and I ask the question, how much is the flux that is going out of any of the sides, for instance, this side? Now, first you invoke symmetry. There is no reason why, since the charge q is at the center, one side of the cube should be different from any other side. So, therefore, whatever is the flux through all the 6 surfaces of the cube should be divided equally by each surface. And what is the amount of flux? So, the amount of flux that I have according to Gauss's law is nothing but charge enclosed q divided by epsilon 0, q enclosed, which is equal to small q by epsilon 0. This is the amount of flux that would go out through all 6 surfaces. So, if you want to talk about one surface, when the charge q is at the center, I get flux through one surface or one face of the cube has to be equal to 1/6 of q by epsilon 0. Okay, that is good. Now, let us ask, what if this charge was not at the center of the cube, but at one of the corners? The symmetry is obviously lost. The symmetry is lost because that charge is at the corner intersection of 3 surfaces. And so, these 3 surfaces are different from the other surfaces. But we can do something better. So, notice that I am interested in calculating the outward flux through this shaded surface. Now, what I do is this: a charge is at the corner. I already know how to solve the problem if the charge happen to be at the center of a cube. So, why not artificially make this charge at the center of a cube? But please note that these surfaces that we are talking about, on which we apply Gauss's law, they are known as Gaussian surfaces. A Gaussian surface does not have to be a physical surface. It could be an imaginary surface as well, because the physical property of a surface never came into our discussion. So, I could be talking about artificial volumes, artificial surfaces. Of course, the charge is real. So, let us look at this. So, what I now do is this, that I put in 8 such cubes. Okay, I put in cubes like this. So, over this cube I put in another cube and put 2 on the side and things like that. So, therefore, this cube, the charge which is shown in red, is now at the center of a cube, artificial cube, but this cube has twice the side of the original cube. Now, as we have just now seen, that if a charge is at the center of a cube, the flux going through any one of the faces is q by 6 epsilon 0. This expression did not depend upon the size of the side, the length of the side. So, whether it is A or it is 2A, if the charge is at the center of a cube, the flux through any face is q by 6 epsilon 0. But I am not interested in calculating flux out of the entire 2A by 2A face. I am only interested in my original face. So, this original face now, you notice, is 1/4 of one of the faces here, and there is perfect symmetry there as well. So, you had q by 6 epsilon 0 through the 2A by 2A face. Through my original face of the size A by A, it is 1/4 of that, namely q by 24 epsilon 0. Let me come to yet another example. So, let me take a uniformly charged sphere. So, there is a uniformly charged sphere containing charge q. Now, if you are looking at, so let me illustrate this here. Supposing this is my sphere containing a charge q, and I am interested in finding out a field at a distance r from the center. Now, if this r is greater than the radius capital R of the sphere, what I do is I enclose this in what I call as a Gaussian surface, which is a concentric sphere of radius r. The electric field, of course, is outward from here. Now, notice that at a distance r, I am interested in calculating the electric field. The magnitude of the electric field is everywhere the same, because it is a sphere. This is the Gaussian sphere, imaginary sphere. So, that my flux is E times 4 pi r square. The direction of electric field is the radial direction, which I will put in by hand at a later stage, and that is equal to q, okay, divided by epsilon 0. So, therefore, the magnitude of the electric field is q by 4 pi epsilon 0 r square, and if you want to write down the electric field itself, then of course, you put q by 4 pi epsilon 0 r square times the unit vector r. Notice this expression is identical to what you would get if all the charges of the sphere, instead of being uniformly distributed, were to be concentrated at the origin of the sphere. Now, suppose instead we have this sphere where the charge is uniformly distributed, radius capital R, but I am interested in finding out the field at a distance r less than r. Now, once again I take a concentric Gaussian sphere of radius small r. The field directions are perpendicular to the surface of this imaginary sphere. So, the left hand side still calculates to be the same, namely E times 4 pi r square. But remember, in our right hand side I had q enclosed. The amount of charge that is enclosed in this Gaussian sphere is not the full charge q, because the volume is less by an amount small r cube by capital R cube. So, amount of charge enclosed is small q capital Q times r cube by r cube. This is the q enclosed, this divided by epsilon 0. So, electric field magnitude is q by 4 pi epsilon 0. Notice it is now linear, r by capital R cube. The electric field direction is still the same. Sorry, this is so let me put this as a vector field. So, therefore, what happens in this case is this, that up to the radius r it goes linear and then it falls off quadratically following Coulomb's law. One more exercise. Let us look at a spherical shell of inner radius a and an outer radius b. Now, what is the field at 3 different distances? First, if you look at totally outside the shell, somewhere in this region, my calculation is identical, because the amount of charge that is contained is all that we have to calculate. I have given that this is a spherical shell with charge density k by r square for a less than r less than b. So, rho is some constant k by r square. So, how much is the total charge? The total charge then is integral rho dq bar. But notice this only depends upon r. So, therefore, the theta and phi integration do not come into picture, and that gives me 4 pi. Angle integration gives me 4 pi, and I have rho which is k by r square, and dq bar which is r square sin theta d theta d phi. The sin theta d theta d phi has been taken care of already in my 4 pi. So, this times r square dr from a to b. So, this is nothing but 4 pi k into b minus a, that is my charge. So, if I am looking at radius r greater than b, the directions are all radial. So, the magnitude of the electric field will be 1 over epsilon 0, the amount of charge enclosed, namely the whole charge, 4 pi k b minus a, okay, divided by 4 pi r square, that came from that E dot d s. So, this also goes as the 4 pi will cancel out, and you will be left with this expression k by epsilon 0 into b minus a by r square. So, once again it is as if the entire amount of charge is concentrated at the origin. Now, let us look at the region. First, let me look at the region r less than a. Now, if r is less than a, I take a Gaussian sphere of radius r, and inside that there are no charge, because it is within the hollow region of the sphere. So, my electric field will be equal to 0. No field in the hollow space. Now, what about a less than r less than b? So, if a is less than r less than b, the calculation is identical, excepting now you have to worry about what fraction of charge is included therein. So, this is the amount of charge that is contained between this sphere of radius small a and this Gaussian surface marked with red. And I can calculate how much is the volume of this, simply the difference between the volume of the radius r, sphere of radius r, and the volume of sphere of radius a, and repeat the same calculation. You will find the electric field is given by k times r minus a divided by epsilon 0 r square times r. So, this is something which this is an application of the spherical shell. Now, let me take yet another example. Let me take the example of a charged sheet, an infinite sheet containing charge, which I will take to be the positive charge. So, this is a sheet which is positively charged. I am interested in calculating what is the field. First, let us look at what statements we can make without actually working out anything. It is an infinite sheet. So, therefore, the field can only depend upon the distance from the sheet. So, field depends upon the distance from the sheet only. The other thing is, if this charge is taken to be positive, then in the upper half of the plane, above that plane, the direction of the electric field will be outward perpendicular to the field. Below the thing, it will be in the reverse direction, because the direction of what is outward changes. If it is above, it is upward; if it is below, it is downwards. So, the electric field is oppositely directed. We will be discussing about it later, but you notice that there is obviously a discontinuity of the electric field at the charged surface. Now, what I do is this: supposing I am interested in calculating the electric field at a distance r, what I do is I take a cylinder. This is a Gaussian cylinder, and let it intersect the sheet. Now, look at the various directions. The electric field on this face here, on the top face, is upward, on the bottom face is downward, on the side faces it is like this, perpendicular to this. Now, so when I calculate E dot ds, there is no contribution from the slanted face, and since the direction of n and the direction of E are parallel on the top and the bottom face, the net outward flux that I get, there are two faces, pi r square each. So, I get 2 pi r square times E, and that is equal to the charge enclosed, which is pi r square times sigma. Sigma is the surface charge density by epsilon 0. So, that the magnitude of the electric field is given by sigma by 2 epsilon 0. We will continue with more applications of Gauss's law and introduce the concept of potential in our next lecture.